coming in. Setor is a fresh PhD graduate from Virginia Tech in computer science and is now a user experience researcher at Meta, Facebook, where he supports UX research for enterprise products. Setor's research focuses on creating a cyber-human approach for capturing and assessing human movement performance. Specific methodologies and frameworks in his research draw on learning sciences, participatory design, and understanding how humans interact with AI. Dr. Zilevu was the recipient of the 2019 William Preston Outstanding Thesis of the Year for Virginia Tech. Congratulations. And of course, his degrees are in computer science and computer engineering, also from Virginia Tech. And he has had experience working at Google, Adobe, and Intel as a researcher and UX designer. So we're really fortunate to have Dr. Zilevu here with us today. And hopefully we'll learn quite a bit about how HCI, AI, machine learning all come together in the metaverse of the future. Thank you.
Good afternoon. Everyone hear me? Can you guys hear me now?
Yes.
Yep. Okay. So good afternoon. So today I'll be presenting to you on my dissertation topic, which is HCI for complex machine learning. So a little bit of background on myself. I've been a lifelong Hokie. I attended Virginia Tech for my PhD, my master's, and my bachelor's degree. I'm currently a researcher at Meta, and I've had internship experiences at the Department of Homeland, Intel, Adobe, Facebook, and also Google. And so what is embodied learning? My research focuses on understanding embodied learning in the real world for complex machine learning systems. And so Hutchins describes embodied learning as understanding the complexity of how humans use their cognitive abilities in a non-simulated environment, such as work or even sports. And some examples that include playing basketball, flying an airplane, or even cooking. And so what we're seeing is that we're moving towards a world where machine learning is going to integrate into a lot of everyday activities. We see it all the time with self-driving cars and automated chatbots. However, there are still spaces where machine learning stays away from, and that's when it pertains to understanding human knowledge. We're all unique. Every brain is different, and every situation that we face is contextual. A lot of human knowledge and behavior is sparse, noisy, and highly variable. Whereas we know that machine learning typically depends on large, good, clean data sets. And so some examples of where machine learning excels at is when we're kind of clicking through Google Chrome and we have to distinguish between whether it's a cat or a dog, or even when we ask Siri to tell us exactly what song is playing. And the reason why machine learning excels at this is because the machine learning model is being trained on good, clean, large data sets. However, when it comes to understanding and predicting human behavior, this becomes extremely challenging. It is very easy for humans to agree on the what, but understanding the why becomes very difficult. So an example I like to use is basketball. If Steph Curry shoots a three, it's very easy for us to understand that he shot a good three-pointer. But if I ask you why, each of us will have different reasons for why the three-pointer was a good shot. And the reason for that is because each of us have our own unique way of thinking about things. And so we know that machine learning depends on good, clean, large data sets. And machine learning models are very good at understanding the what, but not the why. Also, we know that humans are very good at explaining the what, but not the why, thus making it a very difficult problem to create a supervisor for machine learning models. And so what we're seeing is that this is an extremely challenging problem for both humans and machine learning systems. And so in order for this to succeed, we kind of need to understand how do we bring the human to the forefront of this? It can't be a machine solving a human problem. It has to be a human solving this problem in this space. And this is why this is an HCI problem. And so over the last 4 years, oh, they can't see the slides?
Yes. So please Zoom on this computer if you could share your screen.
I should be on this. Yeah, share sound as well. Okay. Okay. And so, okay. And so over the last 4 years, I've worked on creating a human-centric supervisor for understanding both the what and the why for machine learning, because this is an extremely difficult problem when we have sparse, noisy, and variable data sets. And so what I'm going to showcase in this presentation is how I bring human intelligence into complex machine learning spaces where machine learning typically stays away from because of noise, sparse, and variable data sets. And so what we're going to see is that a human-centric design solution is critical. So how do we solve for this? We solve for this by bringing human intelligence because humans are very good at embodied learning spaces. The real expert here is us, the humans, not the computer. Machine learning must learn to leverage human intelligence in order to be successful. Now, I know a lot of people are going to argue, why don't you just let the humans solve the problem and leave machine learning completely out of it? And that's because even for humans, there's spaces that are even too complex even for humans to see or even computationally understand. And we've all heard the saying about how machine learning will potentially replace humans. However, what I'm proposing is that if we leverage human ability and find a way for the machine to complement that ability, we're empowering the human, not replacing them. And so I've worked on creating an HCI design methodology to solve the 3 problems that make complex machine learning difficult for embodied spaces. And so the goal here is to bring human intelligence to synergize with computational intelligence to accomplish 2 things. First, help machine learning overcome the 3 barriers by bringing the human into the loop. And second, by using a participatory design approach, I aim to empower and not replace the human. And so we're walking into a world where health services need to move from a model that is no longer being delivered to now being transmitted. When we look at the aging population, for them to receive the proper care that they need, and for clinicians to be able to effectively assist them, intensive care needs to adopt this model. And for this model to work, it needs to be computed. If it cannot be computed, it cannot be transmitted, thus making it very difficult to have inclusive health. Now more than ever, it is imperative that humans and computers work together within the healthcare space to create computational models that is being transmitted versus delivered to have inclusive health in these spaces. And so what I did was I applied my HCI design methodology into 2 spaces. The first being home-based rehabilitation, and the second being clinical assessment. For home-based rehabilitation, I aim to understand how do we allow someone to do therapy in the home, take that information that is needed, transfer it back to the therapist in a summary version so they can make quick decisions about the patient and then transmit it back in a way that creates better health outcomes. For clinical assessments, assessment of embodied learning is an extremely difficult problem. So much of assessment is tacit and not standardized, making it difficult to get all the information that is needed. And assessment takes tremendous time for therapists. And so what I'm going to showcase is first how I take this methodology that I developed and apply it for home-based rehabilitation, then also prove how it holds true for clinical rehabilitation. And so the way this methodology works is that it has 3 iterative and iterative components. First is where we must transform tacit human knowledge into explicit human knowledge. Then we must make explicit human knowledge computable. And then third, we must use computational power to empower the human. And so I did this by creating first a rating interface and a rating rubric, a capture interface, and an empowerment interface. So far we know that machine learning wants to have good, clean, large data sets. However, in embodied learning scenarios, we have noisy, limited data sets, which are highly variable due to human movement. And so through my presentation, what I'm going to showcase is how we know what machine learning wants, which is good, clean, large data sets. But within embodied learning spaces, we have noisy, limited data sets. What we're going to see is that this is high infrastructure, high cost, and impedes HCI. But when we use the TC methodology that I developed, we can take noisy, limited data sets, include that with a standardized approach, and we can apply it to machine learning and get amazing results. And so here's high-level dive into this methodology. This methodology shows the relation and processes of interfaces that power human intelligence through computer in a non-linear fashion. So this interface facilitates both the human and computer on 2 fronts. First, I developed a rating interface which transforms human knowledge from tacit to explicit. Computationally, this diagram and the rating interface goes into a machine learning HBM model, which then synergizes to increase computational human intelligence. I also created a capture interface, which moves from unstandardized to standardized process for capturing high-quality video data. what we're going to see is that when we bring together both the rating interface and the capture interface, we can then reach a point where we're empowering humans throughout this process. And this is done through an iterative design approach. And so what we're going to see is that through each iteration, the human improves, the interfaces get more refined, and the machine learning gets more advanced, which ultimately means we're reaching a point where we're empowering the human throughout the process. And so when I say humans for this talk, I'm speaking primarily about stroke patients and occupational physical therapists. And so when we look at patients and the patient experience, the primary goal of the patient is to get better and return to a sense of normal human movement after suffering from a stroke. Currently, the process for rehabilitation is a synchronous process. The time, the transportation, and cost make it very difficult and frustrating for many patients to receive the care that they need. However, let's imagine a world where asynchronous approach is available, where patients can perform their rehabilitation at home, which would reduce the time, the cost, and transportation tremendously, and allow patients to receive the same high-yielding outcomes just as they would in the clinic. For therapists, their primary goal is to provide high-yielding outcomes to patients. However, within the clinic, this is very difficult for therapists because it's very difficult for them to have personalized one-on-one time with patients. 15 million people. That's how many people who suffer from a stroke worldwide each year. If we narrow the scope to just the United States, that's equal to someone having a stroke every 45 seconds. On the positive side of this, what we're seeing is that more and more people are surviving from a stroke. However, because more and more people are surviving from a stroke, there are more stroke survivors than there are therapists. And so in order for us to create a model in which therapists can better assist all the stroke victims out there, we need to create an asynchronous approach which allows therapists to be able to adapt and able to provide better high-yielding outcomes for more patients. And so within my dissertation, I aim to answer two questions. First, how do we develop an HCI design methodology that integrates human intelligence with computational intelligence? How do we then transform and make tacit human knowledge explicit, make that explicit human knowledge computable, and then use that computational power to empower the human? And then second, how can we use this methodology to then empower the human versus replace them to reward their participation throughout this process? And so first, what I'm going to showcase is how I use this methodology for the SARA system. And so what the SARA system the SARA system was designed by a multidisciplinary disciplinary team at the Interactive Rehabilitation Lab. What this system is to provide semi-automated cyber-human approach to capture in-home-based rehabilitation. So what the SARA system does is a low-cost system which is aimed at motivating patients to complete the therapy in the home while giving them real-time feedback, which will be similar to what they will receive in the hospital. And so here's a high-level diagram of how the SARA system works. And so it's comprised of 3D printed objects, a custom design map, a web tablet interface, which is the capture interface, markings on the map which indicate where the patient comes from different activities, and 2 low-cost cameras to capture the data. And so the first step within this process is how do we make tacit human knowledge explicit? And we do this through the use of a rating rubric and a rating interface. What I'm aiming to understand here is how can I understand the implicit knowledge that therapists have, and how can I bring that out and make it explicit? And in a way that I can structure their knowledge and represent their mental model. So I begin this process by using a rating interface to facilitate how I understand how therapists think. And so this will first aim to answer the first barrier by which machine learning systems face. And that is, how do we begin to bring out human knowledge that is both explicit and standardized? And so what we're going to see in the next couple of slides is how I take the rating interface to kind of transform this process to accomplish 3 things. First, I aim to bring forth explicit human knowledge. Second, the rating interface will allow therapists to better understand their own practice. And third, it will structure the therapist's thinking within a standardized manner. And all these things are going to happen simultaneously during iterative participatory design approach. And so here's a high-level diagram of the rating interface I developed. And so this was used by occupational and physical therapists to kind of structure their thinking. Qualitatively, it aims to understand how do we structure the therapist's mental model in a way that it can reflect upon their clinical practice. And quantitatively, can we produce good results from this in which we can train a machine learning algorithm system to also now begin to understand quantitatively how the therapists think. So first, in order for us to do that and to reveal the expert knowledge, our team worked with expert therapists to develop a rating rubric and a movement taxonomy. So what we did was we broke down the key movements that stroke survivors would typically do into different segments. We wanted to do this because we wanted to create a standardized structured approach for understanding how therapists think. Our goal here is to understand that because everybody has their own implicit way of thinking, can we create a standardized rating rubric in which we can agree upon the semantic space? And so what you're looking at here is the rating rubric and movement taxonomy developed by expert therapists. What we see is that we broke the different movements that a stroke survivor could perform in the hospital into 6 key components. And what you see below each of the stages of initiation, progression, termination, manipulation, transport, complex manual manipulation, release, and return are the reasons for each of the different movement segments. Afterwards, we needed a way to kind of understand how do we rate and score the system. So we created a scoring scale of 0 to 3, which is widely accepted within clinical practice. A score of 0 means the movement was not attempted. A score of 1 means the activity was either not complete or fully, or the activity was not completed or activity was fully completed, or the upper external collective movement had 2 or 3 elements that show significant impairment. A score of 2 means the activity was fully completed with minimal movement impairment, but the length of execution was unreasonably long, or one element shows significant impairment. And a score of 3 means the activity was completed within a reasonable time with minimal movement impairment. The same scale is also applied to the activity segments, which are the initiation, progression, and termination. And so what I did was I needed a way to kind of understand how can we enact this rating rubric that we developed. And so I developed a video application tool to assist therapists in revealing the expert knowledge. And so what this tool does is that it helps therapists and our machine learning agents structure expert knowledge in a way that's both standardized and quantifiable. And so the outcomes from this is that we want to achieve high inter-rater reliability. When we say high inter-rater reliability, it's an inter-rater reliability of 60% or above on the task, the segment, composite level. You can think of the task as the what, the segment as the why, and the composite level as the reason for the why. And another thing that we want to see is, can we decrease the time in which the therapist might use our interface? The therapist time is very limited. So we understand, can we create a structured process in which the therapist can kind of use our system to reveal their implicit knowledge in a way that'll be quick and efficient? And last, we also want to understand, can we create a quantifiable approach that synergizes human intelligence to assist trained computational machine learning system across all 3 layers? And so here's a high-level diagram of all of what encompasses within the video application tool and the various studies that will encompass. And so what this tool does is it facilitates a way for us to transform tacit knowledge to explicit knowledge to get to a point where it's empowerment. And so through past literature, Fleck and Fitzpatrick's framework, this really laid the model for me to understand how can I kind of structure the therapist thinking to move from tacit to explicit qualitatively, but also quantitatively measure the rate of consistency, the inter-rater reliability, and the time per session. And what we're going to see in the next couple of slides is as we progress throughout each of the different stages from stage 0 all the way to stage 4, the therapist's mental model begins to change as quantitatively as the scores get better. And so we begin here. The video application tool function to movement quality. So within the first iteration, I start with what therapists know, which is explaining the what. So what we see here is that the video application tool is asking the therapist to give the overall functionality score at a high level. And this is why this is a participatory design approach, is because we're allowing the therapist to iterate through what they're accustomed to. So what you're seeing here on the screen is that the therapists have a choice of giving a score of a 1, 2, or 3, and then an option to give the reason for it, and also the ability to comment for why they're giving a reason. And so we're going to measure this quantitatively to understand across the task, and across the segment, and across the composite level, the therapists give a meaning for the score. What we see is that no, they don't. And the reason for that is because they're not trained to focus on the why. If we look at the score here quantitatively, we see the inter-rater reliability across the task, the segment level. We had a high inter-rater reliability on the task level, which was 61%, while on the segment and composite level, it was very low. The reason for that is therapists are very good at explaining the what, but never in their practice that they had to explain the why. And so what we understood from this process was that from a top-down approach, we're very good at understanding how therapists think structurally at the task level. But in order for us to train a machine learning system, we have to understand the segment and composite level. And so understanding that a top-down approach doesn't work, can we switch the approach from the bottom up to understand, if we ask the therapist to start to explain the why, and then kind of funnel down to the what, can we reach a point in which we can have an inter-rater reliability across the task, segment, and composite level across 60%? So in the second iteration of the tool, it is said, what if we went from movement quality to functionality? Our idea is, what if we went up? The therapists give the meaning behind the score, and then we give the score. And so what you're seeing here is that the therapists are now going to select the different reasons that impact movement impairment. From there, a score is generated. And so within this iteration, we had 2 therapists rate over 155 videos of strokes patients perform different activities. We want to understand, does going bottom up work? Can therapists give us enough information from the second and composite level in a way that we can use that to train machine learning systems? And what we see is that this model also doesn't work. And the reason for that is because therapists are trained to observe function. That's what they get paid to do. And also when we see it, also when we see it from the interviews with talking to therapists, we see that the reason why going from bottom up doesn't work is because having someone explain the why and then going to what becomes extremely difficult. And the example I gave earlier, Steph Curry shooting the three-pointer, if I ask you to explain all the reasons why the shot's a good shot versus a good shot, it's not, your brain naturally doesn't think in that format. It thinks from the top up. The brain is naturally focusing from a hierarchy, not from bottom up. And through the therapist interviews, we see them actually explain that through the one-on-one interviews. What they said was that they don't only think about functional problems as a collective of movement errors. That's not how their brain works. And so quantitatively, we see that even within the score distribution. Across the task level, we have a high inter-rated reliability of 83%, while on the second and composite level was 43 and 46%. And the reason for that is because we switched the model of thinking, we compress the top completely. The therapists aren't trained to think in this manner. That's not what they're accustomed to doing. Their learning process involves a top-down approach, and that's what I've been taught to do and think. And so through my research, what I understood is that there's no silver bullet. If my goal is to achieve a high inter-rated reliability across all three layers, I have to kind of redesign an interface in which top-down doesn't work and bottom-up doesn't work. So how can I create an interface in which facilitates how humans think in a way that can bring out their tacit human knowledge, but still provide enough quantitative feedback from machine learning systems? And so this brings us to our third approach, which is the structured decision process. And so what this process does is that we kind of cycle through questions because it's a complex decision model in which therapists have to go through. It's a step-by-step reflection. And so what you see here with the structured decision process is that we're starting at the level of functionality. And this is very clear because what therapists are used to. We started the top-down approach of asking therapists to really explain the what, and we kind of funnel down and go through the why. And the reason why we do that is because the therapists don't feel comfortable going through the composite level. And so by having the therapist first explain the what, and then kind of cycling through these different questions, we aim to understand what is the reasoning for why they're given the what within the structured process. Qualitatively, we see that it works with therapists because for them, they say that by kind of going through the structured decision process, they're able to share more information on movement than they could before through other interfaces. Essentially, what the therapists were stating here was that by kind of going through the structured process, they were revealing their tacit knowledge in explicit format. We see from other therapists who said that by using this video application tool and kind of going through the structured decision tool, it became like a learning tool for neuroclinicians because it brought them back to the original way of thinking. If you remember earlier when I spoke about the rating rubric of how therapists came together to create a standardized structured approach, by using the structured decision process with the rating rubric, we begin to see how therapists can start going back to the original form of practice and understand, okay, this is why I'm giving a score. Here's why, here's the reason for the why. And the reason why that's possible is because by using the structured decision process, we're kind of mapping to the therapist's mental model. We're starting with a top-down approach and pulling down to a bottom-up to what they really don't understand, which is the why and also the reasoning for the why. Quantitatively, we see that we have the best results through our structured decision process. Across the task, the segment, and composite level, we have inter-rated reliability of across 60%. If we look at this from a high level, from all the various studies, we see that in study 3, we have the best and most consistent results. Across the border of task, segment, and composite, we have a strong inter-rated reliability. But what is also interesting to see is that throughout the therapists using the structured decision process, the time in which they spent to learn and use this interface decreased tremendously. And so I stopped at the third interface because I was aiming for a key number of things. One, inter-rated reliability across the task, segment, and movement features. And so what we see at the third level, this produces the most consistent results. And so now what we've seen is that we've reached a point where both qualitatively and quantitatively, we've reached a point where we can understand how therapists think in a way that we can structure the what, the why, and the reason for the why. And what we see also from their viewpoint from the rating process is that they told me that it returned their vision to the smaller nuances of things. For them, by using this tool, it allowed them to really structure the thing in a way that brought them back to the original form of their clinical practice. The way the decision tree was structured, the way the video application tool was structured was that it really allowed the therapist to kind of think through this reflective process of What are the implicit biases that making as I'm rating a different patient? And what this tool brought out was that it brought out their explicit knowledge. And so after bringing out the explicit human knowledge, the thing that I aim to understand is that how do we now make this knowledge computable? And so in phase 2 of the TCE methodology, what I aim to understand is that how do we take all the knowledge that we know from therapists now in a way that can be computable for machine learning system? And so what this process is, and what this does is that it goes from an unstandardized to standardized video capture data process, in which we're capturing high quality video data of strokes and others performing different activities. Our goal here is still the same. We want to increase computational human intelligence. And what I'm going to showcase is how the capture interface is going to synergize with the rating interface to accomplish that. And so here's a diagram of our Setor system being used in the home. And so as you can see, as I stated earlier, there's a 2-camera setup, the mats, and the 3D tablet. And so what we're going to walk through is how this 3D tablet actually captures high quality video data of people using the system. And so here's the capture interface I developed. What it does is that it acts as the voice of the therapist. It walks people through step-by-step instruction of how to perform different activities. First, it makes sure that they're sitting correctly in the right spots. It lets them know which activity they're going to perform. It shows them the activity that they need to perform and how to do it. And once they're ready, they tap the screen to begin. Once they tap the screen, the 2 cameras that you saw earlier are going to turn on and start recording the patient from an activity. Once they're done, once they're done, they tap the screen that they're done performing the activities, and the camera stops, and then they get a high-level feedback. So what I'm going to showcase now is an actual stroke survivor using the capture interface. And so that's a stroke survivor going through and completing one activity of just putting the object down and going back. Once he's done, a high-level feedback is given to him. Either excellent job, good job, or nice try. Each of the scores, each of the feedback that is given back to the stroke survivor represents what we're seeing in the rating rubric. If they got an excellent job, it corresponds to a score of 3, good job, a score of 2, and nice try, a score of 1. What is important to note here is that the stroke survivor didn't know that there was a correlation between the qualitative feedback they're given to the quantitative feedback that we produce. But we see that even for them, they said, they didn't even believe the feedback they were given. For them, once they did a good job, who knows? What we saw from our study was that for stroke survivors, they kind of want to really understand why they're getting the score. Their main objective here is to get better. And so giving this high level of feedback is not enough. They want to understand not only the what, but the why and the reasoning for what they can do to improve upon each of the different activities. So what I learned from this was like, how do we kind of restructure and redesign our thinking in a way that we can capture high quality video data that can fed into machine learning systems to actually produce good quantifiable results that can be given back to the stroke survivor to help them actually improve. And so as a team, we decided that the video quality data that we produced in our first set wasn't good enough. We needed to create a Setor system with fixed properties in order to capture high quality video data. And so what we see here is that we really redesigned our process. We went to a 2-camera setup in which the camera setup was structured and standardized. And what you see is that by creating a structured and standardized process, we can use OpenPose to create a 2D and 3D skeletons of the joint. By creating a 2D and 3D skeletons of the joint, we can generate 25 key points for the upper body. And when placed on top of the actual video data, we can see the overlap. And we can now use the raw video frames for analysis. So what we can do now is take this raw video frame for the analysis, combine it with the results that we've seen from the video application tool, in which therapists are rating and assessing all the different strokes for us to understand, can we build a correlation now to not only empower humans, but also not only empower therapists, but the patients, and also train the machine learning system. And so in the first half of the study, what we see is that by iteration 3, which is a structured decision process, we managed to achieve a high integrated reliability across all 3 layers: the task, the segment, and composite feature sets. And also, we began to see how therapists use a rating interface to build the implicit knowledge and made it as both standardized and computable. And also, we see that from a machine learning standpoint, machine learning can also begin to understand the what and the why now to begin to understand the relationship between movement functionality and movement quality. And this is imperative now because this begins to create a process that empowers the human. And so after working on this for a home-based system, I aim to understand, can I take this methodology and can I apply it to a clinical assessment? And so what I did was I applied it to the ARAC. And the ARAT is similar to the SARA system. As a clinical assessment tool which clinicians observe movements of stroke survivors. However, this system is explicitly focused on movement functionality and assessed through therapist observation. So what this system is primarily focused on is the what and not necessarily the why. And so what we see from the ARAT is that there's three things. One, it focuses on movement functionality versus movement quality. There's a lack of standardization. And two, there's limitations of objective interpretation how a patient performs these tasks. What I aim to do here is understand, can I take my methodology, apply it to completely new domain space, reveal the knowledge in which therapists are using within the ARAT system now to then begin to empower humans and machine learning systems. So what I'm aiming to understand here is that can I bring out the therapist knowledge now for the ARAT? Can I begin to use this to empower patients? And also, can this be quantifiable and trained for machine learning systems? And so within the TC methodology, I aim by using both the rating and the CAP interface together because I took the findings from the SARA system and applied it to this domain space. So what we see here is that I developed a new rating system and capture system for the ARAT. And what it does is the exact same thing. It moves from an unstandardized to standardized process and also transforms human knowledge from tacit to explicit by using the HBM model. In the end, what we're going to see is that we're going to increase computation and human intelligence throughout these interfaces. And so what we see here with the ARAT system is that it embodies a human-in-the-loop architecture to capture therapist knowledge and makes recommendations to assist clinicians. And so what the ARAT is, it has a 4-camera system, which is unlike the SARA system, which has 2 cameras. Everything with the ARAT is standardized, from the box to the camera to even the table setup. And here is the ARAT system being used in Chicago. So this was custom designed by an industrial design team who created this whole systems for patients to go and use the system. So once we have this system, we have the physical property of the system set up, I aim to understand, can I take my methodology now and apply it to the space? And so the first step is to understand, can I create a rubric which can create an agreeable semantic space for the therapist? So what I did here was we work with expert therapists to understand what are the different breakdowns for how you assess and rate the ARAT. What is that tacit knowledge that you guys naturally have? How can we make it explicit? And so by working with expert therapists, we created a whole new rating rubric to understand what is the different breakdowns. So necessarily what you're seeing here is therapists agreeing upon what they're rated, the why for it, and also the reasons for the why, which is also very similar to the SARA system. From there, I also aim to understand, can I create a capture interface in which we can capture high quality video data of patients performing the different activities. My goal here is to synergize both the rating interface and the capture interface together to understand that can we move from tacit to explicit knowledge, and also can we capture high quality video data of patients performing different activities. If we can accomplish both things, we can then begin to train a machine learning system on how to best give semi-automated feedback back to patients. So here's how the capture system works for the ARAT. There's something that's very key to know about the ARAT capture system. For the SARA system, patients were the primary users of the tool. For the ARAT, therapists use the full tool. So the way the system works is that it allows patients to first enter their name, and afterwards they go to the next screen, which shows the different activities that they have to perform. For the ARAT, the patients have to perform 19 tasks, scaling from 1 to 19 into 4 different subsections: grasp, grip, pinch, and gross movement. What is important to note here about the ARAT is that if a patient scores a 0 on task 1, and scores a 0 on, if a patient scores a 0 on task 1 and scores a 0 on task 2, that particular subsection is done. And that's done by Lyell's decision tree, which means the patient couldn't perform the hardest or the easiest task. But if a patient scores a score of 3 on the task, they move on to the grip section, because that means if he can perform the hardest task, which is the first task in each subsection, it means he can perform all the other tasks. When the patient is ready, we have the camera system which starts recording, a timer begins, and then the patient performs the activity, and then the therapist uses it to rate the system and continue on throughout the process. And so what we really aim to understand here was, can we capture high quality video data of patients performing these different activities? And what we see is that we can't, because taking the findings from the SARA system, we understood that by creating a standardized approach, we can use OpenPose again here to understand the different key OpenPose kinematics. And so because we did this and we have OpenPose skeleton, I aim to understand now, can I take therapists all from different backgrounds who have natural tacit knowledge, and can I allow them to use the rating interface now to begin to understand, can we rebuild that tacit implicit knowledge that they have? So I designed the rating interface now to fit the needs of the therapist. And so what you see here now is a rating interface being designed for the clinical assessment. So what you're seeing is that the therapists now are going to rate videos of ARAP patients perform these different activities. What is critical to note here about this is that all of these therapists have never used the system before. With the Setor system, the therapist had 3 years of training to use each iteration of our tool. But when it came to the ARAP, this is our first time ever seeing the tool. And this is the goal, was to understand, can I really create a generalizable approach to understanding how therapists think? And what we see is that, yes, by allowing therapists who have never used the system to now use them for the first time, we have a strong integrated reliability across the task, the segment, and the composite level. This is the results you're seeing here showcase that from therapists with different backgrounds who have never used the system before, we can achieve a strong integrated reliability across all 3 levels. And this is critically important because the therapists all come from different backgrounds. They've never used the system before. They've never had any training to use it before. And so what we begin to see is that the rating interface and the CAP interface synergize together can begin to reveal expert human knowledge. And so now that both interfaces were completed, I aim to understand, can I now use both the rating interface and the CAP interface now to computation increase and empower human intelligence? And so I'm going to showcase how now this empowerment interface now can begin to empower humans, but also train machine learning systems to provoke new levels of reflection. And so what you're seeing here are the scores and the different movement segments from the rating interface. And so when I stated earlier, the therapists have the ability to explain the why for the reason for the score. What this graph is showing patient is their agreement over the total observed, which means for all the different feature sets in which the therapist could observe, what is the percentage agreement that they could have? To put them in context, there are over 15 million different combinations in which a therapist can use within their assessment model. But by using the rating interface, when we focus in on quadrant 4, we see that even though there are all these different combinations and the therapists have all these different tasks of knowledge, within the 4th quadrant, we see that this is a probabilistic space, and that even though they have all these different combinations with human behavior, therapists seem to focus in on these key movement elements that they believe impact impairment. And so what the rating interface showcases now is that because the space is probabilistic, we can then begin to train a machine learning system to begin to understand how to better model the system. So what you're seeing here now in this slide now is the relationship between the explicit human computational knowledge, which is the bottom, versus the machine learning computations. So within quadrant 4, it showcases what the therapists are most focused on when rating the system. What we see by using the OpenPose kinematics and training a machine learning system on it is that there's a direct correlation. What the machine is seeing, which is the composite features average over the kinematic features for difference, is the same as what the human is seeing. So we can now begin to synergize them both together to increase computational human intelligence, because now the machine is beginning to understand the explicit human knowledge that is being showcased. So what you're seeing here in this graph is that the machine now can not only understand the what, but the why, and also given the reasoning for why a patient will perform a task. And so what I'm going to showcase also is this is not only important for the machine, but also this can also empower the humans, and most importantly, the patients and the therapists throughout this process. And so I'm going to showcase a patient performing an activity at the Rehabilitation Lab. I'm going to showcase how we redesign the interface again to really empower both the patient and the therapist.
You're doing amazing. You're doing amazing. Okay, ready, go.
So what you see is that the therapist is really struggling to see what object that the patient is picking up, because the therapist has to see which exact finger they're using.
Where the fingers are from where we need to stand.
The goal of the patient is to take the small marble object using their index finger and bring it to the top.
Bench is just a platform to challenge to get it up there.
Yes, yes.
Goes past midline, I will usually reset it.
There's also the time is very critical here, because the time it takes for them to get it up to the platform matters to them.
The perseverance.
So what you saw there was, like, if you notice that the therapist was really struggling to see which finger they were using to really grab the object up to the top, because if they used any other finger, the score would have been decreased because they weren't performing the task the way they were supposed to. And so one of the feedback that we got from the therapist was that, hey, by using your system, it's very hard to really focus and understand what exact fingers are they using to really bring the object up from the top. It would really be helpful for us to have a zoom in option, because if they really go get up close, they're impeding the camera space. So like, if we're going to rate this off the shelf, we're going to rate this afterwards, is there a way for you to create the system in which we can actually see the exact finger positions, because our human eye can't see it from the distance that we're looking? And so what I worked on doing was taking that feedback to understand, okay, can I now create a viewpoint for the therapist to understand exactly which finger position is being used? So what I did then was I redesigned the video application tool now to include the space in which allows humans to see exactly which fingers, or the therapist to see which fingers are being used throughout the process. What this begins to do now is begin to create an approach and allow therapists to observe more than they could before. So I'm going to take you to a video now in which kind of showcases the future of where this work is going, in which we're creating an approach in which we allow the therapist to observe more than before. So here is someone performing the same task as before. But now you see that the interface now zooms in, which allows the therapist to see exactly which finger joints are being used precisely. So they can now give better feedback and better scores for the system. And it's also done in slow motion too as well, to really allow the therapist to see exactly which finger joints are being used throughout the activity space. As the patient progresses up, you're going to watch the camera view change to allow the therapist to now see the top view, which they couldn't have seen before. And as they go back, the camera view changes. And so this is where we're trying to get to, is to move to a point where both the rating interface and the capture interface are both synergized together. Because what we're going to see is that as the therapists improve their viewpoints and improve their way of thinking throughout these different processes, what we're going to see is that the interfaces are going to get better, which means we can then begin to train a machine learning system to get better, which means we're creating a process where the human is getting better, the interface is getting better, and we're creating better computational algorithms for our machine learning system. And so a question that I get asked a lot is that, why did I not use off-the-shelf interfaces? And that's because these are social technical systems. All three interfaces are developed together to expert human knowledge throughout the process. It needs the human intelligence embedded in the process, and the interfaces needs to be connected. What we're seeing is that health is moving towards evidence-based care, highly individualized, highly personalized, and it's not a one-size-fits-all solution. Every patient is unique. And so by me creating a rating interface and cap interface with the end user in mind, we're really creating a human-centric supervisor in which we're taking into account what the patient needs and what the therapist needs to really create this computational machine learning system. And so what we see is that if you want to bring machine learning to complex places, this becomes very, very difficult to supervise unless the human is at the forefront. You can get people to agree upon the what, and not the why. And so what we created was a human-centric supervisor for training a machine learning system on both the what and the why. What you're seeing here is that both the patient and the therapist are the beginning and end of this process. The machine learning system does not work without the human embedded throughout this. We see that both the capture interface and the rating interfaces are needed to create the algorithm that you see here. Without the capture interface and getting the video frames in a standardized manner, we can't get the OpenPose key points that are necessary to train our system. Also on the therapist side, without the rating interface and creating these therapists rating in a standardized way, we can't begin to understand the relationship between function and movement quality, which understanding the what, the reason for the why, and also the why. And without having that, machine learning systems can create an approach in which they're giving high-level feedback back to patients. What we saw earlier was us first giving a feedback to the patient that said, good job, nice shot, excellent job. What we're working on by creating a human-centric supervisor is that in the future, they're not only going to get that feedback of excellent job, but they're going to get key detailed reasons for what they need to improve upon throughout their rehabilitation, which will allow them to perform the rehabilitation in the home. And so what we see is that, how does this TCE methodology impact machine learning? What I've worked on was I created a standardized process to allow humans to reveal both the what and the why in assessing human movement knowledge. 2, I created a probabilistic relationship between movement functionality and movement quality for both humans and machine learning systems. And 3, I've revealed and transformed implicit knowledge to explicit computable model that could be understood by both clinicians and machine learning systems. And so throughout this, here are the kind of the key insights that I've seen through my research for HCI for complex machine learning. And first, through an iterative participatory design approach, we are beginning to see how computational human intelligence and computational machine learning improves as we move from tacit to explicit knowledge. Second, good inter-rater reliability and rater consistency is necessary to ensure high-quality data that will be appropriated at both the task and segment level. And then 3, as humans develop and refine their work on the body spaces, this methodology will allow interconnected interfaces to adapt to best support both humans and machine learning systems. So over the last 4 years, what I really worked on creating was this human-centric supervisor Which can be applied to machine learning is to really understand and reveal tacit human knowledge and bring forth into explicit in a way that is both standardized and computable.
This is so fun. Thank you.
No problem.
So sorry, Bob, I totally stole your. Thank you so much. I used to teach a class where we would talk about the continuum from not knowledge to expert knowledge. And so I love what you're highlighting here as a potential for helping people really speed up perhaps that process of gaining an appreciation and understanding of the ways in which tacit knowledge, someone doesn't know how to say, can be learned and taught. And I'm curious, where else would you like to see this applied? This is one really awesome iteration, and I can imagine a gazillion others. So I just would love to know, where do you want to see it go next and why?
Yeah, one of the things that I want to see go next, I was actually talking about this with a friend a couple of weeks ago, was for things like also social reform, and that came up in a meeting like earlier today. And the reason for that is because when we look at when a judge hands down like sentencing for someone, there's so many biases that go into place, there's so many tacit knowledge that comes into it. But when we take this methodology and we apply it within that space, we can kind of create a standardized approach where we kind of create kind of like fairness in a sense, where we know that, hey, by training these different systems or training these different judges to understand, here's kind of the process that you're kind of going through throughout your the way in which you're sentencing somebody. We can apply this methodology and have a machine learning get that feedback. So we're kind of creating better equity in the sense of that we know that the fairness and that someone is getting a sentencing, it's fair because we're applying a methodology which is trying to remove those biases.
Okay, thanks. I don't know. Oh, okay. Yeah, hey, thanks. Oh, it's very bright. Yeah, my question is about your the rating system. So when you have to pick either 0, 1, 2, or 3, does that assume? I mean, it kind of seems to be assuming lots of confidence that the therapist is confident that it should be a 2 or a 3. It doesn't capture any of the uncertainty. And I'm wondering if and then those numbers lead directly to your inter-rater reliability, which are really important numbers in your system. So I'm wondering if by not asking for or not allowing the therapist to input any amount of uncertainty, just assuming pure certainty on the therapist's part, does that lead to inter-rater reliability numbers that are maybe not accurate?
Yeah, so that's a great question. So we're actually allowed to actually put in the uncertainty, and that's the why. And so when we look at the video application tool, first at the high level, they give that score of 0, 1, 2, or 3 within that first iteration. And they kind of go through and check, okay, this is the reason why I'm giving a score of 1, 2, 3. So we kind of understand this is your baseline for it. What we saw is that within that first iteration, that doesn't really work because they're not going to get the reason for the why, because that's not what you're trained to do. But within our third approach, the structured decision process, what we kind of do is kind of synergize both the top-down and bottom-up perspective. And so the score that you see being generated at the end, that's by the therapist understanding, and we work throughout the co-design process. And so what you see is that in the third process, we're kind of going through this process of cycling through all these different questions. What you're really seeing with the questions, we're starting from this top-down approach. They're not giving a score. They're just giving us kind of this question based on the task performed. Yes. Was this performed in a reasonable amount of time? No. What was the different reasons for it? Give the reason, and then the score is generated. So the score generating out at the last end of it, and so we have all these different reasons for it beforehand to get to that process.
Cool. Okay, thanks.
Questions? So I just asked the Zoom folks if there's any questions on Zoom, and I was gonna see if anyone's tracking YouTube. Should I just hop onto the YouTube channel?
No questions there.
No questions. Let's see what's happening on Zoom. Okay, so I do have a question. And I was hoping Mike Barron would be here today, but he isn't. Okay. The design choices you make from everything, right? How many cameras, their viewing angles, the types of objects, their shapes, everything is a choice that leads you down certain paths in both the experience and the measurements you could get from quality. And this is like an extremely highly complicated design space, and therefore you have to have certain design principles that guide all these things, right?
Yeah.
But I've always worried that the data that comes from experiments is shaped by all these choices that have been made ahead of time. Again, nothing like it's not a deal breaker, but I'm just wondering, how do you envision any, at least from the perspective of ML, if you develop an ML model that works off of movement data under these conditions, its generalization to a slightly different deployment with a slightly different camera view, slightly different objects and their shapes.
Yeah.
So how do you imagine the shaping of the data from these design choices influencing ML's performance?
Yeah, that's a great question. And so to really kind of capture what you're saying, you're asking how did the design decisions we make, how did it influence the machine learning system? Yeah, that's a great question, because when we first started off this process, we really went through like kind of like in the wild, right? Can you guys still hear me on Zoom? Okay, yeah. So we kind of went through this kind of process in the wild where what you saw at Emily was kind of just us going saying, can we capture the data just period, right? Without really having a standardized, unstandardized approach and just really going through it. And what we saw was that it was very difficult for machine learning systems to kind of get these different OpenPose kinematic, kind of get through this process. And so the design choices we made were also not only influenced by the human, but also the machine learning system in mind too as well. When we kind of went through that standardized process where, okay, we have a 2-camera setup where it's 6 feet apart on each side, the therapist goes and sets us up, it takes 10 minutes, 5 minutes. That's all done by design, because by kind of creating that process, it really influences the data we're getting from the machine learning system. If the camera system and everything is not standardized, the process isn't kind of structured away for ML systems, it becomes extremely difficult throughout the process.
I mean, assuming you're getting 3D data from those things, like, isn't the table is the reference, right? Like all their motions are in relation to the table. You could come out with another camera that's like maybe a single camera that captures perfectly good 3D data, and then yeah, shouldn't it still work?
Yeah. So one of the things that that's a great question. I hear that a lot too. Is like you can add more cameras to it. The more cameras you add, the more data you're going to get. Or also, we have to keep in mind that these systems are going to be in place in people's homes. And so, how would you feel if there was like multiple cameras in your home? The buying from the human standpoint, like, I don't feel comfortable because I feel like I'm always watched. And so by kind of using that 2D camera set that we have, that was done by design, because we really wanted to create a system in which the patients feel comfortable using, but also can produce great results for the machine learning system. With the ARAT system that you saw, which is a clinical system, where we had those 4 different camera angles, that's because that's in the clinic. And so patients will feel more comfortable using it in the clinic. But when we kind of transition back into the home-based system, we have to understand how can we capture high quality video data given a limited camera set. Yeah.
Any final questions from anybody? Did you say yes? Oh, okay. All right. I think that was the last question then. Let's just double check on Zoom. Otherwise, this was a great talk. Okay, lots of all good here's. All right, fantastic. So thank you so much, Dr. Zilevu. This was a fantastic talk. We shall just hang out here if you don't mind, and we'll keep talking. But yeah, we can turn the Zoom channel off. Thank you so much. Yeah.